Hello and welcome to the session. In this session, we will discuss normal approximation to binomial distribution. Suppose we have a deck of cards. The probability of drawing a heart from the deck of cards is 1/4. If number of trials is 10, we can easily find the probability of drawing at most 3 hearts using binomial distribution. Here, number of trials, that is n is equal to 10, probability of success P is equal to 1/4 and probability of failure Q is equal to 1 minus P is equal to 3/4. Using binomial distribution, the probability of drawing at most 3 hearts, that is x less than equal to 3 successes, is probability of x less than equal to 3 equal to summation NCX P raised to power x Q raised to power n minus x for x equal to 0, 1, 2, 3. So we can calculate it easily by putting the values. Now suppose there are 150 trials and we have to find the probability of drawing 80 or fewer hearts. Now here n is equal to 150, which is very large. And if we use binomial distribution, we get probability of x less than equal to 80 is equal to summation of 150 cx 1/4 raised to power x into 3/4 raised to power 150 minus x for x equal to 0, 1, 2 and so on till 80. This is not easy to calculate. So, we cannot use binomial distribution. A better approach is to use normal distribution to approximate the binomial distribution. Now we see how to decide when normal distribution is used to approximate binomial distribution. If we have a binomial distribution where n is equal to number of trials X is equal to number of successes P is equal to probability of success on single trial. And Q is equal to 1 minus P is equal to probability of failure on single trial. Where NP is greater than 5 and NQ is greater than 5. Then X has a binomial distribution that is approximated by normal distribution with mean mu equal to NP and standard deviation sigma equal to under root NPQ. So we can summarize, if random variable X follows binomial distribution with parameters N and P, and if NP is greater than 5, NQ is greater than 5, where Q is equal to 1 minus P, then X can be approximated by random variable Y following normal distribution with mean NP and variance NPQ. For example, in a binomial distribution, we have N equal to 14, P equal to 0.62 and Q equal to 1 minus 0.62 equal to 0.38. We find NP and NQ. NP is equal to 14 into 0.62 equal to 8.68 and NQ is equal to 14 into 0.38 equal to 5.32. Both NP and NQ are greater than 5, so we can use normal distribution. With mean mu equal to NP equal to 8.68 and standard deviation sigma equal to under root of NPQ, which is equal to under root of 14 into 0.62 into 0.38, which is equal to 1.816 approximately. Note that as n becomes larger and larger, the approximation becomes better. Graphically, as n is increased, the histogram or bar chart will approach a normal curve. Let us now discuss correction for continuity. Binomial distribution is a discrete distribution and normal distribution is a continuous distribution. To represent a discrete distribution graphically, we usually make bar charts and to represent a continuous distribution graphically, we usually make histograms. In order to compare the binomial and normal distributions, we draw a bar chart that looks similar to histogram, and for this, we widen each bar by 0.5 units on either side so that each is still centered on an integer value, but the bars now touch each other. When we do this, we are making a correction for continuity. Each bar will have an area proportional to the probability of the integer on which it is centered. Let us see the following figure. Here we have probability distribution graph of random variable x. This is for binomial distribution. To convert it in continuous distribution, we move each bar 0.5 units on either side so that they touch each other. See, when we moved 0.5 units left and right of x equal to c, C has now become the midpoint of the bar drawn. The area under this bar is equal to P of, that is probability of, x equal to C. This shows probability graphically. Now suppose we want to calculate it algebraically. Now see, this area of bar drawn at x equal to c lies between the points c minus 0.5 and c plus 0.5. So the probability when x is equal to c is approximated by the interval c minus 0.5 and c plus 0.5. So probability of x equal to c is approximately equal to probability of c minus 0.5 less than equal to y less than equal to c plus 0.5. For example, we want to find probability of x equal to 14. By normal distribution, it is approximated to be equal to probability of 13.5 less than equal to y less than equal to 14.5. Thus we summarize, to find the probability of a discrete random variable x, that is the number of successes, by converting to a continuous random variable y, we will follow the following rules. Probability of x greater than equal to c is approximately equal to probability of y greater than equal to c minus 0.5. Second, probability of x strictly greater than c is approximately equal to probability of y greater than equal to c plus 0.5. Third, probability of x less than equal to c is approximately equal to probability of y less than equal to c plus 0.5. And lastly, probability of x less than c is approximately equal to probability of y less than equal to c minus 0.5. For example, probability of x strictly less than 20 is approximately equal to probability of y less than equal to 20 minus 0.5. Here we use the last rule. Probability of x strictly less than c is approximately equal to probability of y less than equal to c minus 0.5. This implies probability of x strictly less than 20 is approximately equal to probability of y less than equal to 19.5. Similarly, probability of x less than equal to 20 is approximately equal to probability of y less than equal to 20 plus 0.5, which implies probability of x less than equal to 20 is approximately equal to probability of y less than equal to 20.5. Now, to find this approximate probability using normal distribution, we will convert normal variable y into standard normal variable z, where z is equal to the value minus mean upon standard deviation which is equal to y minus mu upon sigma. And using table of standard normal distribution, we will find the required probability. Let us see the following example. A random variable x has binomial distribution with parameters n equal to 200 and p equal to 0.85. Use a suitable approximation to calculate probability of x equal to 174. To approximate its probability, we will use the following procedure. We have n equal to 200 and p equal to 0.85. So, q is equal to 1 minus p, which is equal to 1 minus 0.85, that is equal to 0.15. Now we calculate NP and NQ. NP is equal to 200 into 0.85, which is equal to 170, and NQ is equal to 200 into 0.15, which is equal to 30. Both NP and NQ are greater than 5, so we use normal distribution to approximate the binomial distribution. We have to find probability of x equal to 174. So we convert random variable x to normal variable y using continuity correction. We know that probability of x equal to c is approximately equal to probability of c minus 0.5 less than equal to y less than equal to c plus 0.5. Here c is equal to 174, so we have probability of x equal to 174 is approximately equal to probability of 174 minus 0.5 is less than equal to y is less than equal to 174 plus 0.5. This implies probability of x equal to 174 is approximately equal to probability of 173.5 less than equal to y less than equal to 174.5. Thus, random variable x follows binomial distribution with parameters n and p is converted to random variable y following normal distribution with mean np and variance npq. That is, random variable x follows binomial distribution with n equal to 200 and p equal to 0.85 is converted into random variable y following normal distribution with mean 170 and variance 25.5, where mean of normal distribution mu is equal to np is equal to 170 and standard deviation is equal to sigma is equal to under root of npq, which is equal to under root of 25.5, which is equal to 5.05. Now we will convert y into standard normal variable z using z equal to value minus mean upon standard deviation that is equal to y minus mu upon sigma. So, probability of 173.5 less than equal to y less than equal to 174.5 is equal to probability of 173.5 minus 170 upon 5.05 less than equal to y minus mu by sigma less than equal to 174.5 minus 170 upon 5.05. Now 173.5 minus 170 upon 5.05 is approximately equal to 0.69 and 174.5 minus 170 upon 5.05 is approximately equal to 0.89. So probability of 173.5 less than equal to y less than equal to 174.5 is equal to probability of 0.69 less than equal to z less than equal to 0.89. Let us draw its figure. This is a standard normal curve with mean 0 and variance 1. Mean equal to 0 lies in the center. 0.69 and 0.89 are to the right of 0. This is the point 0.69 and this is the point 0.89. Let us draw vertical lines here. The region between these 2 points is the required probability. This is to be shaded. Using table of values of normal distribution, that is area to the left of z, that is P of z less than equal to z, we will find its probability. From the figure we can see that probability of z1 less than equal to z less than equal to z2 is equal to probability of z less than equal to z2 minus probability of z less than equal to z1. So, probability of 0.69 less than equal to z less than equal to 0.89 is equal to probability of z less than equal to 0.89 minus probability of z less than equal to 0.69. From the table of standard normal distribution, of the form probability of z less than equal to z, we find probability of z less than equal to 0.89 is equal to 0.8133 and probability of z less than equal to 0.69 is equal to 0.7549. So, probability of 0.69 less than equal to z less than equal to 0.89 will be equal to 0.8133 minus 0.7549, which is equal to 0.0584. Therefore, probability of 173.5 less than equal to y less than equal to 174.5 is equal to probability of 0.69 less than equal to z less than equal to 0.89, which is equal to 0.0584. Thus, probability of x equal to 174 is approximately equal to 0.0584. Thus, in this session, we have learnt how to approximate binomial distribution using normal distribution. This completes our session. Hope you enjoyed this session.